I'm here doing day 6 of Advent of Code. I have not yet recorded days 4 or 5, and I've just solved them in my free time. But I figured I wanted to get back on track, and I want to record day 6 and do day 6 fresh. So it's not a kind of prepared solution, or I've not had time to think about the problem. My explanations for day 4 and 5 will be coming. They're a little bit more complicated. Day 5 was a real challenge. Just to give you a little hint, I got it down, so I solved day 5 in order of milliseconds. Right, I think I got it down to about 76 milliseconds or so, but before it took 35 minutes to run. So day 5 was a real fun challenge. But anyway, enough about day 5. We're on to day 6. It's a fresh problem. I have not read this yet. So the ferry quickly brings you across island to island. After asking around, you discover this normal large pile of sand near here, but you don't see anything besides a lot of water and a small island where the ferry is docked. Grand prize is an all-expenses-paid trip to Desert Island. That's where the sand is from. Sounds about right. You manage to spin up as a competitor in the boat race just in time. The organizer explains it's not really a traditional race. Instead, you will get a fixed amount of time during which your boat has to travel as far as it can. And you win if your boat goes the farthest. Okay? As part of signing up, you get a sheet of paper, which is your puzzle input, that lists the time allowed for each race and also the best distance ever recorded in that race. To guarantee you win the prize, you need to make sure you can go farther in each race than the current world record holder. The organizer brings you over to the area where the boats races are held. The boats are much smaller than you expect. They're actually toy boats, each with a big button on top. Holding on the button charges the boat, and releasing the button allows the boat to move. Boats move faster if their button was held longer, but the time spent holding the button counts against the total time. Okay, so it's a kind of min-max problem. You can only hold the button at the start of the race, and boats don't move until the button is released. Okay. So, this document describes 3 races. Okay. The first race lasted 7 milliseconds. The record distance in this was 9 millimeters. Okay. I'm just going to say seconds in meters. It doesn't really matter if the units are both in the millis. So, you have 7 seconds to go 9 meters, okay? The second race lasts 15 seconds, and it goes 40 meters. And then the third race is 30 seconds and goes 200 meters. Your toy boat has a starting speed of obviously 0 meters per second. For each whole second you spend at the beginning of the race holding down the button, the boat's speed increases by 1 meter per second. Okay, so your acceleration effectively is, well, it's not even acceleration, but it's just, yeah, you get 1 extra meter per second. So if the race lasts 7 seconds, you have a few options. Don't hold the button at all. That is, hold it for 0 at the start of the race. The boat will move. It will travel 0. Of course, you could hold it for 1, and then it will go 6 by the end. You could hold it for 2, and then it will go 10 because you have 5 extra seconds. You could hold it for 3, and then you're an extra 4 seconds. So it's, yeah, remaining times the number of milliseconds you hold it from. So really, like, I think I have a pretty simple way to solve this. Okay, so what's it actually asking? Since the current record is 9 millimeters, there are 4 ways you could win. Okay. At the second race, you could hold the button for at least 4 milliseconds and at most 11 milliseconds to beat the record. And you have 8 different ways of doing that. This one you have 9 ways. Okay. Number of ways you can beat the record in each race. Multiply these values together. Okay. So let's get my puzzle input. I think I have a real... Oh, wow. That's really short. It's going to be like a trick question? This seems pretty easy. All right. But I guess the previous days of Advent of Code have been really hard, so maybe this one's just being nice. Okay. So let's make our files. Okay. So day 6. Let's use our core library and let's write our main function. I guess we need to sort of parse these. Yeah, what am I trying to do? I'm trying to pull the input and I was looking in the wrong spot for it. So let's pull this up over here. I'll close out of my terminal. All right, so I guess to parse this, let's really just do this really cheaply. So let's say you have your input and you're just gonna load inputs day 06. I'm just going to have this. I'm going to have a time string and a dist string for distance string. And I'm just going to simply bisect this string, which I don't know if I've done yet before. And I forgot the order of the arguments here. What bisect does is it simply splits a string into 2 parts divided by the first instance of the character. So by splitting on a new line, that's basically going to give me this as one string and then this as the other string. Bisect is actually how split iter works. The function that we've used a lot is just repeatedly calling bisect on whatever delimiter you passed in. So it's pretty simple. So we get our 2 strings. I'm going to use the advance function. And I'm just going to say we're going to advance by like this many characters. Oops. I thought that button would work, but maybe not. So let's paste. Whatever. Okay. That many characters. Doesn't really matter. Just so long as I distance. Okay. So I'm going to advance both of them. And this is the dist string. So then I need to just make, excuse me, the 2 arrays. So let's do that. I have a function from a different day that I think I will use called split into ints, which just takes a string and splits it into all of the integers, which it's simply just doing a split on space, map, and then collect. This one actually will need to have a filter to filter on the things that are not empty, because this one we're going to have some extra spaces in here. So split on things that are spaces, do that, and then I actually don't even need to collect them. I actually want this to be an iterator over I64, so then I can get each one. And then I'm going to use a very handy function called zip. So what this does is it takes 2 iterators and I'm going to pipe this then into iter collect, and then print out. I'll just print out the result right here. What iter zip does is it takes 2 iterators and it prints out, or it basically takes them and makes a pair out of them. So I'll close this because I think we have it all parsed correctly now. It takes a left iterator and a right iterator, and they can be of different types, and it produces an iterator of pairs over those 2 types. And it just simply gets the next thing out of both of them and then makes a pair out of them. And that's all it's really doing. And so by doing this, what we're effectively saying is like, take the first thing of the time string and the first thing of the distance string and pair them together. And then take the first thing, the second thing, you get the idea, right? So this is cool. So now, really, it's just about finding which of these we can beat, right? Like, now I was kind of thinking about it. Let me go back to the problem. So like, if you hold it for 0, you go 0. If you hold it for 1, you go 6, because it's basically the number of seconds you hold it times the total duration minus the number of seconds. So if I pull up a Desmos calculator, I can kind of visualize what I'm talking about here. If I can type, that would also be very useful. So basically, if x is the number of seconds you hold it down for, our equation basically looks something kind of like this, right? If we can hold it down for 7, or like our time limit of the race is 7 seconds, what we're looking at here is basically just this parabola, and we're trying to ask how many integer points are above, in this case for 7, it'd be 9. So as it said before, right, 2 is greater than 9, and so it's the 3 case, the 4 case, and the 5 case, but then the 6 case is lower than it. So there's 4 ways that you can beat it, right? Because you have 10, 12, 12, 6, or 10, 12, 12, 10. Close out of that. So this is effectively what we're looking at, and we're just asking for how many points is this greater than a particular region, which could be, well, I guess in this case the problem said 9. So for how many points is it greater than 9? And I think it's going to be a strict greater than, no, not greater than or equal, because you don't want to tie the record. So then, yeah, obviously we can see in this range, we go from 2 to 5. So effectively, what we just need to compute is this boundary, right? The left and the right-hand side, and then do some kind of clever rounding, and then take the range of how many things there are, right? So let's think about how we get the left-hand side, right? I'm just going to plot this as well so we can get the full visualization again. So how do we get this left-hand side? Well, we have our equation, and we're asking for when does it equal 9, right? Let's subtract off 9. When does that equal 0? And then let's just, I don't know, let's factor this out a little bit. So that's ax minus x squared. Yep, so we're keeping this right. So I'm going to make this, I'm going to make it into a standard polynomial. And then let's just do the quadratic formula. Negative b, which is negative a in this case, plus or minus, so do the plus case, the square root of b squared minus 4ac, so that's really going to be a plus, well, minus 4, I'll type this all out and then it'll make it make sense. And actually, I don't want to do b, I don't want to do 9, I want to do b, make this a variable. And then all of that, which I should have made the division sign before, but it's fine, all of that over 2a, which is really just negative 2. Cool, so that is what is going to give us our solution. Of course, then we can do the negative case, and we will get the other one. So just some quadratic formula stuff. So like we can have our solution 1, and that's going to be that, and then we can have our solution 2, that's going to be this one, and then our boundary really is just, I'm guessing it'll always be the ceiling of S1 and the floor of S2, if I were to guess. And then really, actually, if we do this really easily, we can do the ceiling of S2 minus the ceiling of S1. And that should always give us the right answer. Okay, so I realize I've kind of solved this problem in Desmos, but let's try it out. So let's do a time of 30, and we have a duration of, or a distance of 200. So this says 10. And is 10 the correct answer? No. No. So why is that? It's because 10, and they did this on purpose, the 10 case here is actually a tie, right? And so we actually don't want a tie. We want it to be, so I'm going to define a function g, and I'm going to say it's going to be x plus 1 if the ceiling of x is equal to x. Otherwise, it's going to be the ceiling of x. And I think I have to remember how to write this. I think it's actually this way. Yes, okay, so I don't want to plot this, but this is really the function that I care about. I think it's always the ceiling of that minus the g of this one, I think. Because it also lands on 20, but I think 20 would beat it. We'll have to see. We're going to have some off by 1 issues, I think. Let's try the middle case, just for the fun of it. So it's 15 for the time and 40 for the other thing. And that says 8. And that looks right to me. So let's take the solution that I guess I've made in Desmos, kind of accidentally. Let's put it into our actual code here. So we have our pairs of numbers. So these are our cases, really. And, well, I can actually I'm just going to keep writing this in this iterator style, which I don't know if I've actually done on a video before, but I think I have. I don't remember, though. Basically, it's taking the left-hand side argument and passing it into the first argument on the right-hand side, which for most of these functions is actually just like an iterator. And so most of these functions take an iterator and return an iterator, especially if they come up here. So like flatten takes an iterator and does something and returns an iterator. Zip, we've looked at, takes iterators and returns an iterator. Skip while does all of that. And so these iterators chain really nicely. And so we can actually just kind of do it this way. So I'm going to take my pair of numbers, right, which in this case is this A and B, where A is the first one and B is the second one. And I just need to, really, I'm just going to call a function that I'm going to call solve. It's just going to take these numbers, do the quadratic formula, and then return the integer, right? I'm just going to have it return this number. We'll go write our solve function. And then we need to multiply them all together. And so to do that, I need to make a 64-bit 0, which currently in Onyx, this is how you have to do it. But I have to write it that way because it cannot be inferred. It's a little confusing, but it's all right. So what this fold function does is it's just going to take initially 0, which I actually don't want 0, I want 1. And then it's going to repeatedly call this function with the previous result, which I'm actually, to make this clear, I'm going to call this ACC, also called the accumulator. It's going to take the previous result and then the next thing out of the iterator that's generating things, and it's going to multiply them together. And so you can think about if you do this over an entire list of numbers, you're going to find the product of all those numbers, right? It's a very functional way of writing it. You could also do this with the for loop, and it would be just fine. So that's going to be that product, and then I'm just going to print line, because that's just going to be our solution. So let's write that solve function, and let's think about what it's going to take. Well, it's going to take our race. I'll call it race. That's a good name. And it's going to have the input of a pair, right? Because that's what zip returns. It returns a pair of numbers. And then it's going to return, I'll say an I64. That's just going to be our solution. All right, so we're going to have, I'm actually going to call them A and B. And they're going to be 64-bit float numbers. So the way we access them is we just use the first and second properties on here. Now, as you see, we're getting an error because I want these to be floating point numbers, and I am, right now there's integer numbers. There's a couple ways I can solve this. One is I can just kind of cut this out and put in a proper cast. Oop, I actually want to cast to F64. And actually, I like the way this looks, so I'm gonna keep it that way. All right, so I have my A and B, and now I just need to kind of write my solutions. So S1 is negative A plus math dot square root of A times A. And then let's kind of think about this. 3 negatives, so it's still going to be negative. 4 times b. If I simplify this, right, this negative can go away because this negative goes away. Right? Yep. Okay, so then that negative can go away because that negative goes away. Okay, cool. So there's that, and then all of that times negative 0.5. I just prefer writing it that way. All right, so then S2 is exactly the same thing, except we have a minus sign. All right, and then we need that little g function, which I'll just call it g. And it's basically the following. If math.ceil of x is equal to x, return x plus 1, because then we didn't actually beat it. Otherwise, return math.ceil of x. And then I will use that function here. So I'll say math.ceiling of s2 minus g of s1. And then we also have to convert this into a 64-bit integer, because that's what we want our result to be. Because we're counting the ways to do this, but we're kind of doing it in this indirect way where we're using a parabola. All right, so if I run this, well, I get this number. And I guess I'm hopeful that this is the right answer. It might not be. That's okay. It's too high. Okay, so that means we're probably including a case where we shouldn't be. So the beauty of this being such a small test case is that I really could solve this in Desmos. So maybe let's look at the numbers that they gave us and see if there's any trickery that's going on here. I'm going to just change the y-axis to be like up to 1,000. And then maybe we'll pull this over. Okay, so over here, it looks like you would have to do for 6 seconds, and then over here you'd have to do it for 47 seconds. Okay, so this said 42, which I think is right. Let's think about this. So, let's also add a little thing in here. It's just going to be a little dumb thing that is going to print out our x value and then immediately return it. But this way I can see the number that it's getting. Okay, so my solution online says 42, but my actual computation is 43. So that's a problem, because I don't think that's correct then. Okay, so did I write something incorrectly? I don't think so. Ceil of S2 minus G of S1. That looks right. And this cast should never really round it. I'm going to make sure that that's the case, though, because maybe this cast is rounding it up or down. It's going to print that, and then, yeah, whatever, let's print this. Nope, this cast is, these are perfectly right on the nose, so that's good. That's what I expected from doing a ceil. Let's print just a rounding up. Okay, so we never hit that case. So then where's the discrepancy? I guess we just keep printing a lot of things. So let's print off our S1. Let's print our S2. Ooh. Oh. Parentheses are important. Parentheses are very important. 42, yeah, that number looks a little bit better. And it's a little bit smaller, which is kind of what I would expect. So let's clean this solution up and hit the right keys to copy things. Let's go over here and paste it. Let's try again. Woo, got it right. We just had some unfortunate order of operations there. That's all right. All right, so part 2. Let's make this full screen. The race is about to start. You realize the piece of paper the race times and record distance you got earlier actually just had very bad kerning. There's only really one race. Ignore the spaces between the numbers and the lines. Okay. Okay. So, interesting. Which I can imagine for people not doing this in the parabola way, now you have a lot of numbers to check, right? Because now this is a really big number. But we're using this with 64-bit floats and some parabola math, so I think we should be good to go. So let's do that. I'm trying to think of the nicest way, because this is the part we're going to change. We're not going to split into ints. I'm trying to think of the right thing to do. We can still zip it. We just really want a function that join into large int. So that's going to take our string. It's going to return an iterator because it has to for how we're going to use it, but we're actually just going to return a single thing. And so there's a really easy way to do that. So really all I'm going to do, I'm actually going to go onto my Onyx docs. Ooh, I mistyped that at some point, and for some reason it thinks that that's what I want to do. And actually I don't want to go to this one. I want to go to the packages. Ooh. Packages/core, which I could also get to from the website. And I want to remember what some of my string functions are. So string. I thought there was a one that you can remove certain elements. Read until, read alpha num, copy, trimming, which is not quite what I want. There might be something in slice because it might be a useful thing like that. There's remove. Oh, there's that. Oh, there might actually be one in the array because it's something you'd more do in a dynamic array kind of thing. We could filter elements. Here, array.remove removes all instances of elem from the array. Uses equal to test for equality. Perfect. The only slight issue is that we don't have a array here, or a dynamic array. We just have these strings, which are actually just a slice of bytes. And so what we're going to use is actually something from the string function called to dynster, which is not apparently documented. But what to_dynster does is it takes a string, it takes an allocator, which defaults to the context allocator, and produces a dynamic array of bytes, also called a dynster. So I'm going to call this input, I don't know, and it's going to be this dynster type, which is a dynamic string, which is basically just a dynamic array of bytes, meant to encapsulate the idea of a string that can change. So I'm going to use string.toDynster on S, and that will give me that dynamic string. And then I will use the array.remove function from input, and I'm going to remove all of the spaces. And then I'm going to say my result is just parsing that thing as an integer, and then I will return that result. Now, I have to return an iterator, and so I actually use the function iter.single, which, as the name kind of suggests, it just yields a single value, and then it stops. That's all you have to do. For posterity, because toDynster does allocate, I will actually call the delete function on my input, which is a very overloaded function for how to delete almost anything. And so in this case, it will end up calling the function to free a dynamic array, which I believe is array.free. It will get to this point where it frees that automatically. Not really automatically, I have to say it, but using defer in this way is really nice. Okay, So I think that should work. And so now for part 2, we are actually just going to use join into large int of the time string and the dist string. And I think we're good to go. That seems way too small. That seems way too small. I gotta try it before I even debug it. Yeah, it's not right. That's kind of what I figured. Okay, let's do some stuff here. So let's first so one thing I'm going to do is just effectively comment that part out. And then I'm going to collect, and then I'm going to print. Comment that out by just giving it an empty iterator that isn't going to do anything. Okay, so that was wrong. Okay, so I only got 53,250. Okay. Yeah, I only did the first test case. So why is that? I guess I'm going to print line input at this point. Oh, what? Why doesn't array.remove work? Is there a bug in the implementation? That would be unfortunate. So if we're going through the array, yeah, why is this not working as I thought it should? Well, that's unfortunate. I'll have to look into that. But for right now, I noticed this filter function, which will also work. So the way I'm going to do this is I'm going to say filter. I'm going to provide it this code block. And I'm just going to say where v is not equal to space. Oh, is that broken too? What the heck? Are both of these functions not implemented correctly? I'm losing my voice too, which is also no good. Okay, I don't know what's wrong with this. So I'm going to use a last-ditch effort that should work. I'm going to iterate over the input, but I'm going to use it as an as iterator. And so the reason I'm going to do this is because dynamic arrays, when iterated over like this, give me a, what am I trying to say? They allow me to do this kind of cool thing. I'm going to say if the character is a space, I can use the #remove directive, which, like the name suggests, it will remove the thing. Now, the reason why it has to be like this is because it's a feature of a dynamic array, and so, or of an iterator when you're iterating over as a dynamic array. And so it's basically just another function you can overload to add this functionality, and it should work. I know I've used this one. There we go. Ooh. Now that doesn't look like the right answer, but do we at least get the right parsing? 53916768. 250133010811025. Okay, so that looks right. Where are we running into an issue? My first guess would be in this square root, but let's just print out some stuff. So let's print out S1, let's print out S2, let's print out the result. Let's see what we're doing here. Oh. Huh. Huh. Yeah, what we're doing wrong is we're not solving the problem. This number looks plausible. Perfect. Okay. I just forgot I kind of commented that out, and I was just running the wrong code. Good times. All right. So, remove all those prints, and that looks like it's working. And so now our two solutions are basically, if you uncomment this one, you're doing solution 1. If you uncomment this one, you're doing solution 2. That was a good day. I can imagine for people who did an iterative solution, iterating over all the numbers. When you get slapped with giant numbers like this, that would be no good, but, right, it's just a parabola. And so we just solve it with the parabola. So that was a good day. I enjoyed that problem. Now I just need to get my voice back and actually record days 4 and 5. So I'll start working on that.